Okay. So now we will resume our class, on this PyTorch. So last time we finished here. So the ResNet, this is the abbreviation for residual network. Okay. So normally, if we stack more layers in deep architecture, the performance, if let's say this might be the A layer structure's performance during the training, and also this might be the testing error for A layer deep architectures. And if we stack more layers, their performance, their error might be decreased during both training and testing. Okay, but if we stack more than 20 layers, it tends to their accuracy, their error tends to increase again because of the vanishing gradient effect. Okay, so the learning, the training does not happen properly, so the network accuracy become less than the shallower network if it's more than 20 layers. So this was kind of the problem in deep learning, but this ResNet is solving that kind of problem. So this is the original deep architectures we learned so far. So we stack normally some convolutional layers with some activation layers in between. So from the original input X, we calculate our output HX by involving some convolutional layers in the middle. But in the residual block, we involve the skip connection. This is called as the skip connection. So the effect of this is, let's say the output, the h of x is just applying this kind of f function. Let's say this is the function large f. Then the new function would be, we can write it as this. This is the skip connected original signal, and this is the function we calculate through this stream. So previously, the thing we have to do is we need to calculate this kind of gradient by differentiating the output with respect to their input. And for overall deep architectures, we have to calculate this. And also in the worst case, we have to calculate this gradient for differentiation for the final output with respect to the first input. But the thing is, let's say this y is the final output, and let's say this is the initial input. Okay, so let's say this is the very, very deep architecture, having more than maybe 20 layers. Then we have to calculate this, and this is composed of individual layers gradient, which might be less than 1. Okay, and if we multiply the floating values, which is less than 1, more than 20 times, this simply goes to 0. And because of this, we cannot properly calculate the LD setup. This is the proper direction where to update the parameters. So this simply goes to 0, and we cannot properly update the parameters. Okay, if this goes to 0, then parameters, new parameter would be same as the old one, because this would be 0. So there's no parameter update. So the training does not happen properly. But if we apply this ddx to both sides when constituting the output by adding some skip connected signal, then now the new gradient would be that is +1. So now the signals are becoming at least around the 1. Okay, so and this becomes more stable and does not simply goes to 0 anymore. So we can calculate this DLD sector more stably if we skip connect the original input signal to here. Okay, are you guys following this? Okay, this is important. And because of this, the resonate previous the deepest architecture without this residual connection was the VGG or the Google LUNET, and they could stack only 19 layers. And also if we stack more than 20 layers, it does not work properly because of the vanishing gradient effect. But if we stack the 34 layers with the skip connection like this, then thanks to the residual connection, their gradient does not vanish anymore. So we can stably train this deep architecture with the residual connection. Okay, so that's the very simple scheme, but very effective scheme proposed in the ResNet. Okay, and this is the implementation for the ResNet. So we first have to define several convolutional blocks. So this is very simple, actually. We can specify which activation function we will have after the convolutional layer. We can specify it in the conv2d function. Okay, so this class are using defining the convolutional layers to have the activation layer afterwards. Okay, so we have to, this might be ReLU, and we have to specify it from the upper class. Okay, and this is the input and output dimension of the convolutional layer. And also this is different stride, okay, stride 1 and 2. So the class name is depending on the stride, okay. So we have to define this kind of convolutional layer. And here we do not have activation function, okay. There's no argument for the activation function here. So this is the only convolutional layers without the activation function afterwards. And we have to define two types of convolutional layers with different stride, okay? And here we define convolutional layer with different kernel size with the activation function, okay? So we define actually 5 different types of convolutional layers. And then this is important, we define bottleneck layers, okay? So this bottleneck layer is actually this type of layer, okay? So what bottleneck layer does here is they first define layers sequentially stacking 3 types of convolutional blocks, and then sometimes they use the downsampling, or sometimes they don't involve any downsampling. Okay, that's the thing happen here. So when I will explain this first. Okay, so we involve 3 sequentially stacked convolutional layers here. So when inputted, X is inputted, we first input the input signal X towards the convolutional layers, and then add the original signal X. Okay, this is the layers having the residual connection like this. So this is the H of X. This is the H of X defined. okay? And then, I mean, this is h of x, actually applying x with the 3 sequentially stacked convolutional layers. And then we add original signal x after that, okay? So actually this is defining this kind of function, okay? And then sometimes we have to secure this original signal's dimension is same as the h of x. So we have to sometimes apply the downsampling operation and add the downsampled signal, okay? The downsampled original signal, we have to apply that, okay? And also here we do the similar thing, okay? So this is the bottleneck with some stride, and this is the bottleneck without stride. Okay, this also doesn't use with stride. Okay, stride is 1 here, and stride is 2 actually here. Okay, and also this is does not use any downsampling, but these 2 are using the downsampling. So anyways, we define 3 variants of the bottleneck layers here, but the core operation is defining this, okay? And then for defining the overall ResNet, in the first layer, we just apply the convolutional layers with the activation ReLU layer and also the max-spring layer. And then afterwards, we only apply the bottleneck layers, okay? It might be looks like this. So the first layer is defined without any residual connection, but later, all the subsequent layers are bottleneck layers with the residual connection, okay? So that is actually defined here, okay? And at the last, we apply the average splitting and apply the FC layer. So this is our forward function, okay? So are you guys following this? Okay. Easy, maybe. So this is the ResNet architecture, okay? Actually, we learned okay. So we learned this, okay, previously. So previously, the first architecture before 2012, these algorithms are not deep learning algorithm, but they are shallow learning algorithm based on the SVM. But after 2012, this AlexNet architecture comes out. Every image classification, their state-of-the-art accuracy was accomplished by the deep learning architecture. And in the year of 2012, the AlexNet with the A layers come out. And after that, here, 2014, the researchers are proposing deeper architectures with 19 up to 19 layers and 22 layers, whose name is VGG and Google LUNet. We already learned about this. And in the year of 2015, the architecture whose name is ResNet comes out, and it actually outperforms the human performance in image classification task, okay? So here it has 100 up to 152 layers, okay? So, I mean, this ResNet is until now frequently used for visual recognition tasks, okay? So this was the review for the CNN architecture. And now we will learn more techniques for deep learning training. Okay. So So this is something we learned so far. So I mentioned that any differentiable layers could be in between the input and final output, and we have to also define the loss function L. And when defining the layers in between here, we have to define some differentiable layers. And differentiable means we have to calculate these two gradient. Okay, that's the meaning of differentiable layers. Okay, if we can define these two things, then that layers are differentiable. So this means given for individual layer, we have to define their differentiation of output respect to their input, output respect to their input. And the next important thing is we have to define the differentiation of output respect to the parameter sector of that layer. So we have to be able to calculate these two gradients to define the differentiable layers. Okay, but thing is, if there is no parameter, then we can skip this actually. So for individual layer, if it doesn't have any sector to update, then we can omit that. Okay. For example, pooling or activation layers like ReLU and tangent hyperbolic or sigmoid, they don't have any parameters to update. Okay. So in that case, we don't have to calculate this for this. Okay. We don't have to calculate this. Okay. But anyways, if there is any parameters to update inside the function f, then we have to be able to calculate this parameter update rule. Okay. And that should be calculated for calculating actually this rule. So this is denoting DLD sector, where to update the parameter sector to minimize the loss. Okay. And this sector is updated. Okay. And we call this two line of code to automatically calculate the gradient for each node, and also calculating this formula once. Okay. Okay. So this was the PyTorch code we have learned. So last quiz, I somehow, insert this line of code here and ask you something about this long code. Okay. So this is making all the gradient to 0. So if you insert this here, then after calculating gradient, it makes gradient to 0 and then update to zero direction. So the update is not happened. So you have to make it in the right order. Okay, the code have to be in the right order. Okay, and anyways, this is the thing we learned. And this is also to show more about the difference between stochastic gradient descent and gradient descent. So their formula, this is the gradient descent formula. They are actually same for gradient descent and stochastic gradient descent, but different thing is gradient descent, they update this once after seeing all the data. Okay, so let's say this X and Y are containing all the data. Okay, maybe because their overall data size is small, they can contain X in the one single variable and can update this once for the whole data. But if we have more, if our data set is large, then we have to approach it like this. So from the data loader, we have to load it with the small batch size for example, maybe 32 normally. So maybe the overall data size might be very big, like this, 100,000 data samples, the overall data, training data might be. But we can load it with these 32 images one by one. And then we can calculate this parameter update rule for this small number of images, okay? Then this might be different from what have been done here, okay? So here we see overall, maybe let's assume we can contain this number of samples in here, okay? Maybe in reality, there might be memory error, but let's assume we could, load all this amount of data in the X and Y variable. Then this might be happen once when we calculate this for all the data, okay? But here we calculate this every batch, okay? So this is the difference between stochastic gradient and gradient descent, okay? So I mean, in the sense that gradient descent is calculating the optimal direction by seeing many data, it goes one optimal direction. Sometimes, I mean, some may think this might be better in practice, but in practice, SGD performs better than the gradient descent because, I mean, this is the illustration of the parameter update of the gradient descent, and this red lines are update for the stochastic gradient descent. So this black is showing it is approaching the optimal point smoothly, but stochastic gradient descent, it is going to the optimal point rather in the noise manner. And also their final location is different from that of the gradient descent. But thing is, this optimal point is optimal for training data, okay? So, but the thing is, our parameter sector, or sometimes we denote it as the W, the model's parameter have to be tuned for unseen testing data. Okay, our model have to perform good for the unseen testing data, but I mean, if we approach it like this, the model could overly fit it to the training data. Okay, so SGD in practice is not regarded as optimal in the respect of the training data, but in practice, we test our model on the unseen testing data, which is different from the training data. So in practice, SGD performs better than GD. There's not much difference, okay? And actually even better than GD. And also stochastic gradient descent is more effective, more efficient during the training, okay? So that's what I want to re-explain here. And also when explaining the AlexNet, I explain about the dropout, okay? So, and for explaining that, I may have to explain this concept, the overfitting phenomenon. So, I mean, overfitting, it happens due to a lot of reasons, okay? So this GD is also one use of the GD is also one reason, okay? It may lead our model to overly fit to the training data, okay? So, I mean, overfitting, this is the phenomenon that the model performs good for training data, but if it performs worse for testing data, then it's called as the overfitting phenomenon. So this graph is showing the error according to the number of epochs. Okay, each epoch we see whole data, actually the training data. Okay, during training, if we see one whole training data, it is called as one epoch. So this is meaning the number of times we see whole data during the training. So this means the training goes, and as training goes, the training error. This line is showing the training error. Sorry. This curve is showing the training error during the training. So the model see the training data and it become to perform well for the trained data it already seen. But after some time during the training, the testing error, it also decreased, but sometimes the model shows this kind of tendency. So here you can observe that for the training data, the model is becoming to perform better, but for the testing data, the model is becoming less than before, okay? But our aim is having the best accuracy for the testing data. So this is not that desirable situation, okay? We call this as the overfitting phenomenon. The model performs good for the training, but it does not perform well for the testing. So this is not desirable situation. So we call it as overfitting and try to relieve this during the training. And maybe this is the example that explains the overfitting phenomenon well. So when making bad, you have to see, you have to make the model a bad model. Rather than deep learning model, we are assuming that we are making some bad model that fit to unseen human shape. Okay. So when you make the bad have to be well operate for unseen humans. Okay. So that's when we say we made the good bad, then that good bad may be comfortable for every human. Okay. But if you make the bad like in this, mimicking the shape you lie in the bed. So this bed might be good for only one person. Okay. So this one person might be similar to the training data. Okay. So seeing just one person, if we make the bed like this, then this bed might be uncomfortable for most of the unseen humans. Okay, so this is kind of the good example for explaining the overfitting phenomenon. So we have to make the deep learning model which performs good for most of the unseen testing data. Okay, and have to avoid this kind of overly fitted model. Okay, so and overfitting, when we explain overfitting in the context of the deep learning, we normally see this kind of figure. So this circle and this X, this cross is cross symbol and circle symbol, they are denoting some samples, individual samples with circle label and cross label. Okay, and given this data, we can learn some model that can divide these samples into two classes. Okay, so I mean this is the straight line, which means the model is like this, using only the linear operation. If we use only linear operation to separate these two data, then I mean this is the most simplest function. Okay, and this is might be more complex than this kind of function, but involves more higher order functions. So I mean, if we involve this kind of curve, then it means the complexity of the function inside our overall function is becoming higher. Okay, and if we involve more curve inside the curve, then it is meaning that this n, the order of n for the polynomial, that becomes a lot higher. Okay, so it means this is for this we are trying to fit the data with the simplest linear function, and this is having the moderate complexity functions. Okay, we try to fit the data with the moderate complex function, and here we are trying to fit the model with the data with the very complicated function. Okay, so but I mean this circle and the cross in these graphs are training data. Okay, they are denoting the training data. Okay, and even though we fit our function as overly fit to this training data, when the testing data comes to this function, I mean, here, this X could be some noise in training data, okay? And in practice, the testing data might have circle for these regions, okay? So, I mean, if we make our model overly fit to the trained data, then it cannot actually avoid this kind of label noise, okay? So, I mean, and let's see the overall figure again, okay? So maybe you can feel like that this kind of curve is kind of the best curve that actually avoid overly fitted to this kind of noised samples. Okay, so I mean this is the best situation we can fit our model. Okay, but this is the model actually overly fitted to the training data, so it can be affected by some noise data. Okay, and this is too simple, and I mean we have to train further towards this more complex function. So this is called as the underfit situation. Okay, so for the underfit, we have to fit more for the model to make it to the normal fit, and we have to actually start training here. Okay, at the normal fit to avoid the overfit phenomenon. Okay. So this is the three types of things. Okay, and there are actually many ways to prevent this kind of overfitting phenomenon. So, I mean, these two might be a representative way to prevent the overfitting phenomenon. One best way and one very simple way is increasing the size of your data. okay? So, I mean, making your network overfit to million scale data, I mean, let's say this is the world scale data, okay? I mean, if the model is overfit to the data we can see in the world, then it is the best case actually, okay? I mean, let's say this is the, if we can get, if we can collect the world data, this world data means, this world data means the data we can get, all the images we can draw, all the possible images we can draw is this world data, okay? If we can make the, if we can make our model overly fit to this world data, then our testing data might be also belonging to this world data. So the model will perform well for testing data as well, okay? So the ideal case, okay? But the thing is, we cannot collect all the possible data, which is the world data. So always our training data is also subset of this world data. But we normally say if we collect million scale data, which is actually very large, okay? Very large. If we can make our model overfit to very large data, which is in the million scale, then actually testing data have the higher probability than before to be a subset of this large scale training data. So because of that, I mean, if the training data, their size is in the million scale, then I mean, making this model overly fit to training data could be a way, actually, way to achieve the good accuracy in the testing, okay? So anyways, I mean, the naive method is increasing the size of the training data to make it in the million scale. That is actually good way to prevent the overfitting phenomenon. Actually, it overfit to the training data, but training data is already very big, and the testing data have the high probability to be the subset of the training data, so it performs well for the testing, okay? So we can actually prevent the overfitting, okay? And the other way is the having the validation data, which is the independent set of the data. So we learned only the training and test data, but we define another validation data. So we normally do it like this. So we, from the original training data, we use only their 80% and randomly split them into the validation set, okay? This proportion might be arbitrary, you can define it, but actually most of the original training data you reuse for the training data, but small portions of the data, you can use it as the validation data. And then what you do is like this. So you draw the curve like this, the number of epochs and error curve, and measure the training error, at the same time measure the validation set's error, okay? Validation set, they are not used during the training. Only 80% of the original training data to update the sector, only 80% of the training data are used. And using the updated parameter, you can test on the validation data set, which is the small portions of the training data, which is not used for updating this sector. And then after some epochs, you can see this kind of phenomenon. then this is indicating that you have to stop here your training. Are you agree with that? Okay, so because the validation set, which is not used during the training, their errors are increased again. This is the indication of the overfitting. Okay, so you have to stop your training here. Okay, and I mean the sector obtained here you will not use because it performs well only for the training and not for others. Okay, and you may use the models trained until here. Okay, I think this is called as the early stopping scheme. Okay, seeing the validation curve, validation error curve, you can stop the training when the validation error becomes increased. Okay, this is the early stopping. So actually, these two are, I mean, the most intuitive. I mean, the most simple way to, I mean, prevent this overfitting phenomenon. Okay. And another scheme was dropout proposed by this AlexNet architecture. This is actually frequently used inside the deep learning architecture. So I already explained this, but I want to re-explain this with some proper figure. So somehow to prevent this dropout is also proposed to prevent the overfitting phenomenon. So even with these two schemes, the overfitting is hard to prevent. So I mean, the AlexNet additionally proposed this dropout. Maybe you can see here they are using dropout in the FC layers. Actually, this is the final FC layers. And here they are using this dropout layer. So it on purpose randomize your network to prevent your network overly fitted to the training data. Okay. So, and during training, they randomly, for each epoch, it randomly turn and turn off the sum of the node, okay, and turn on this node only inside the deep architecture. This is the layer, denoting the layer. And actually in PyTorch, you can specify the probability of turning on, okay, turning off. Okay, this indicates the turning off probability. Okay, but the thing is, during the evaluation mode or the test mode, it is not used. Okay, so dropout, this is just multiply one operation during the testing, but during training, it randomly turn off some of the node with probability of this. Okay, so and this prevent your network overly tune the train data because your structure, the network structure is randomly adjusted during the training. So your network could not overfit to the training data. So this is what dropout does. And the other important idea is this is also proposed by the data augmentation, okay, the AlexNet. I already also explained about this. So data augmentation, this is increasing the number of data. So this is very simple scheme. So this is showing one sample of the MNIST data. I don't know what this is, maybe two, I don't know. But you can maybe apply some flipping operation to make the new samples, okay? And maybe this is applying both, I don't know. I mean, you can apply this kind of color jittering or horizontal flipping or random rotation this kind of random transformation on the original image data to make the original data to this kind of transformed data. But the thing is, their label is actually same even though they are transformed. So that is what data augmentation does. So you will use all of this augmented data as the training data during the training. So if you make the 3 times augmentation, then your overall training data is 3 times than before. Okay, so this is very simple way to make to increase the size of the training data. Okay. And this is another example for simple data augmentation. So you can flip the images, and this, even though they are horizontally flipped, they are containing the same object, so their labels are not changed. And also, if you crop the original image, making this, their labels are also not changed. Okay. So so even though you crop the original image and apply the flipping, the content is not changed. So you can augment the size of data using this simple cropping and flipping. Okay. And maybe if the original size is 246 by 256 by 256, and the cropped image is 224 by 224, then their margins are 32. So you can actually crop the original image this amount of time. And if you flip the image, then you can actually make this number of augmentation for one original image. So this is very simple way to increase the size of the training data. Okay, and also even though you apply the color variation on the original patch, then their content is not changed. So you can use both for the training data. Okay, you can apply a lot of this color variation to the original sample, and actually you can increase the training data with a factor of infinity, okay, during the training. And this is actually one graph showing the effectiveness of the data augmentation. So this is the best state-of-the-art. Green is denoting state-of-the-art architecture for each multiple tasks, okay? And this is the CNN features, okay, trained by the ImageNet dataset, okay? This pink graphs are showing the deep architectures pre-trained by the ImageNet. But this is the this red bar is showing the graph. I mean the accuracy obtained by the CNN architecture pre-trained by the ImageNet with the augmentation scheme. So I mean you can observe that this augmentation is very simple scheme, but you can compare to the pink graph bar. You can see the same architecture using the same training data, but with the augmentation, you can significantly raise the performance for multiple tasks. So use this simple data augmentation, okay, during the training. And this is the actually the same code as before. And another way to increase the data set size might be, I mean, manually label and collect some data by yourself. Doing some manual labeling you can also increase the data size. Okay, so this MS COCO data set published it in ECCB 14 is the one example to collect such large scale data sets. So it has this amount of image and containing this amount of object with 91 categories. And they actually use for manually labeling for these images, they have to obtain this kind of image level labels, semantic labels, and also this kind of bounding box label, okay, and also this kind of segmentation-wise label, and also they also have to note this kind of instance-wise segmentation mask. So this blue is this is denoting the semantic segmentation mask. So their color is same across the same object. This is all cow, all sheep, maybe. This is dog, and this is human. So the color indicates the semantic class. But here, this is the indicating the instance-wise. So if their instance is different, their colors are different. Anyways, they are similar, but anyways, they manually label this kind of thing using Amazon Mechanical Turk. Okay, so we can use this kind of crowdsourced framework for manually label this kind of large scale data set. Okay, so this is very simple way to, I mean, not simple, but anyways, the doable things we can collect the large scale data set. And this is showing some interesting graph. So these red dots are experts, their performance, and this is the general worker, their performance, and recall and precision. Maybe I will explain it later, but you can think this is some accuracy for their annotations. So this is higher is better actually, but the experts, they are in the middle for the recall, but their precision is quite high. And in general worker, their recall is quite spread and precision is lower than the experts. So anyways, we have to involve expert for annotating this kind of data set, and also they involve a expert worker whose annotation it might be correct with over 50% probability. Then if we, I mean, this 0.5 might be the probability of having wrong labels. And if we multiply them 8 times, then we can gradually reduce the probability for having incorrect labels. Anyways, using this kind of crowdsourced framework, we can label the data. Okay, so this is the example for getting the data. And also the other way to get the large scale data set might be using some graphics rendering engines. So you can see that this kind of images are not realistic data we capture by our camera. So, but they are some rendered humans with some arbitrary background images. So we can actually train our network using this kind of synthetic data as actually. So the merit of this synthetic data is we can simply render it using the graphics engines. So we can make infinite number of training data, and also when rendering, we know which graphics engines we are using. So we somehow already know which labels they are containing. Okay? So this synthetic data, their merit is no effort, almost no effort for secure labels. And also we can make infinity number of samples. Okay. That's the merit. So for training deep architectures, we require million scale data. So the synthetic data is kind of the way to secure such million scale data. Okay, so this is the example. So because this is rendered from some game engines, 3D engines, this is also the image rendered from the engines, 3D engines. We already have this kind of dense segmentation map for each 3D model. So we can, without much effort, we can secure this kind of segmentation annotation with these rendered RGB images. Okay. Okay. So for later part, I will explain maybe that in later class. So the thing I want to tell is this. So this is the code, the training code. So we already learned about these loss functions, the BCE loss, and the cross entropy loss, and the mean square error loss. We already learned about these things. These two are used for the classification task, and this MSC is used for the regression task. And for the CNN architecture, we can define it here. Okay, we can manipulate this. The only thing remained is how to load this X and Y data. So we learned that this could be the synthetic data, or we can collect some realistic data and with the manually labeling the images. Okay, so we can do this kind of variant. And another thing remained is our optimizer. So we are using the SGD. Okay, from previous slides, previous lectures, we only use this stochastic gradient descent or the gradient descent, but this has some problem. So maybe later we will learn about which kind of optimizers we can have except for this GD and SGD. So that might be this momentum and also this Nesterov gradient update and ADA grad and RMS probe and ADAM. So normally we use ADAM. This is more advanced optimizer. So compared to the SGD, this ADAM is providing better features for training. So we normally use ADAM nowadays. So we will learn what is the merit and demerit of these optimizers in the later class. Okay. Okay. For today, let's finish here and let's see again in Wednesday. Thank you.